In this video, we're looking at two more examples for the ratio test. And before we do the example, let's just sort of remind ourselves how the ratio test actually works. We're doing here the limit of one term divided by the previous term. So that's an plus 1 divided by an. And we are looking for what that limit's going to be. If that limit is small, if the limit is less than 1, we have convergence. If the limit is large, if it's larger than 1, we have divergence. And then unfortunately, if that limit is exactly equal to 1, our test fails. It is going to be inconclusive. Okay, so for this one, let's go and take a look. Okay, these factorials we said last time, okay, those are huge indicators that we should be looking at the ratio test because the other tests simply, aren't going to work out nicely. So for this one, we can set up our limit as n goes to infinity, and we're looking at an plus 1 over an. And we plug in here, we do an plus 1, and this is going to become sort of a real mess very quickly. We have 2 to the power of n plus 1 times n plus 1 factorial divided by 3 times n plus 1 multiplied by 2 times n plus 1 factorial. Okay, now wait, that is just our an plus 1. Then we have to divide by an, but we know instead of dividing by an, I'm just going to multiply by the reciprocal. Okay, so I'm going to take an, I'm going to take the reciprocal, which means I'm going to flip the numerator and the denominator, and I'm going to multiply by that. So here I multiply by 3n, 2n factorial, divided by 2 to the n times n factorial. And this is the limit that we have to do. And at this point, if you're not comfortable doing the ratio test, this is definitely the point where you're going to start to panic and you're going to say, I have no idea how to do this limit. But for the ratio test, the same thing is going to happen every time. It's going to look like a complete mess, but you're going to start the first step by just saying, I'm going to group all of these similar terms together. So for example, I have these exponentials. I'm going to put them together. I have this sort of factorial, and I'm going to group that with this factorial. I have this 3n plus 1. I'm going to group that with a 3n. And I'm going to take this factorial and group it with its corresponding 2n factorial. Okay, so we're going to group all of these together, and then we'll actually take a look at how to deal with the limit. Okay, and hopefully it'll be much more manageable at that point. So absolute value, the first thing, let's say we have 2 to the power of n plus 1 over 2 to the power of n. Then I have n plus 1 factorial over n factorial. Then we have, let's say, 3n over 3 times n plus 1. And we have 2n factorial divided by 2 times n plus 1 factorial. Okay, and actually, let's do ourselves one favor. Let's rewrite this last part as 2n plus 2 factorial. So I took all of this right here, and I expanded it, giving us 2n plus 2. Okay, so now this whole thing is in absolute value, and really, rather than doing one very complicated limit like this, what we're going to do instead is sort of deal with 4 different, much easier limits. Okay, so the first one here, this is actually the easiest one. We could just simplify it. There's no limit here involved. I'm just going to get rid of this, and it's just left now with 2 to the power of 1. Okay, so we have at the beginning the limit as n approaches infinity, absolute value, we just have 2 to the power of 1. Now, n plus 1 factorial over n factorial, we saw in the last video how we deal with that. We take the larger factorial, we rewrite it in terms of the smaller factorial. So that's n plus 1 times n factorial over n factorial. And then we're going to cancel the factorials with each other, leaving us with just n plus 1. Then we have 3n over 3 times n plus 1. And that one we're going to leave. It doesn't really need to be simplified. It's going to be fairly easy to deal with no matter what. But now the last one here, another set of factorials, we rewrite the larger factorial in terms of the smaller one. So I leave 2n factorial alone, and I have here 2n plus 2 times 2n plus 1 multiplied by 2n factorial. Okay, so that is our denominator, the larger factorial, rewritten in terms of the numerator. And now I can simplify it again in the same way. I get rid of my 2n factorials. Okay, so let's see what we have left over now, and hopefully this limit is going to be a lot easier. Okay, we still have this 2 at the start. We have an n plus 1. We can actually cancel that n plus 1. So here, let's cancel this n plus 1 with this n plus 1. Okay, so here, let's do that in orange. Let's say that one and that one are going to cancel each other out. And now we are left here with just 3n over 3. And that's going to be multiplied by 1 over 2n plus 2 times 2n plus 1. And now, looking at this limit, you could do it a couple different ways, okay? One way is definitely just to do L'Hopital's rule, okay? And another way is just to look at the degrees. So this is degree 1, this is degree 2, which means our limit is going to be 0. But if you didn't know that and you wanted to check using L'Hopital's rule, then I'm going to expand the denominator. Okay, this term right here, I don't want to have to do a full product rule on the denominator, so let's just expand that. We end up with 4n squared. We're going to have 6n plus 2, and now we can do our L'Hopital's rule. The numerator was just 2 times 3n, so it was 6n, and the derivative of that 6n will just be 6. In the denominator, I have a 3, okay? And actually, I could have canceled that 3. We should have. That would have been nice. But let's just leave the 3 alone for now. I have 3 here, and I'm going to do the derivative of this term. Okay, so that's going to give me 8 multiplied by n plus 6. And now, as n approaches infinity, I'm definitely going to get 6 divided by an ever-increasing number. And that limit, as we said before, that limit is just going to go to 0. Okay, now, specifically, we need to remember, though, that we are here to do the ratio test, okay? So that limit being 0, we care about that because that is a number that is less than 1. And that means that our series, AN, is going to be convergent by the ratio test. Okay, remember that for the ratio test, if that limit exists and that limit is less than 1, then your series is going to be convergent, and that's very much what we have right here. So when you're doing these limits, okay, remember it's very important. It's going to start off here as a complete mess, but then you're going to rewrite it. You're going to group all of these terms together into smaller, easier to manage limits, and you're going to simplify them as much as possible. And after simplifying them, you should end up with something like this, which is going to be a much more manageable limit to do. Okay, so that's one, definitely more complicated example for a ratio test, but let's do one more. Here we have our final example for the ratio test, and this one again, we have that factorial. We also have an n to the n, which is a weird term. So here, that factorial is sort of leading us to think that we should be looking at the ratio test. So let's set up our limit as n approaches infinity, an plus 1 over an, and let's see what we get. An plus 1, we have n plus 1 to the power of n plus 1 over n plus 1 factorial multiplied by the reciprocal of an. Okay, so again, we're going to flip that an term, which is going to give us n factorial divided by n to the power of n, and right away you're going to get this ugly limit, but we're going to remember that we group these terms together. We're going to try to simplify them, and then we'll see what we end up with. So I'm going to have n plus 1 to the power of n plus 1 divided by n to the n multiplied by n factorial over n plus 1 factorial. And we know by this point that I'm going to rewrite the larger factorial in terms of the smaller factorial, because then we can cancel those out. And at the same time, I recognize that here I have n plus 1, and here I have n plus 1 to the power of n plus 1. So let's cancel this out, and that's going to cancel with this 1. And then you might say to yourself, hey, this is going to work out now very nicely. I end up with a fairly straightforward limit. I have n plus 1 to the power of n divided by n to the power of n. And that is a limit that I would say is, unfortunately, it looks deceptively easy, but it is definitely not. Okay, so first off, it's indeterminate. We have infinity divided by infinity. Okay, and you could go and try to use L'Hopital's rule, except doing the derivative of something like this requires logarithmic differentiation. Remember you're trying to, differentiate something like x to the power of x. So that's sort of a problem in itself. We don't want to have to go and do L'Hopital's rule. The other thing is that maybe you're looking at this and you're saying, well, I'm going to use that shortcut that we've talked about. I know that the degree of the numerator is n and the degree of the denominator is n. And so the limit is just going to be the ratio of the coefficients, okay, of the highest powers of n. Now, that is unfortunately not usable here, okay, because we're actually taking n going to infinity. Okay, we don't just have, degree 5 over degree 5. Our degree is actually changing. Okay, so this is far more bizarre a limit than you would initially think just looking at it. Okay, so what we're going to do is actually just a very nice little bit of algebra here. Okay, I can rewrite this with a common exponent. I'm going to rewrite it n plus 1 over n to the power of n. And now actually you're going to realize that yes, this was a little bit more bizarre than we thought, because this base is going to go to 1 and the exponent is going to go to infinity. What we have here is an exponential indeterminate form, 1 to the power of infinity. So, we know how to deal with these exponential indeterminate forms. Okay, we went through that whole video, but we actually, for this one, don't even need to introduce a logarithm. Okay, we don't need to really work on that exponential indeterminate form, because this is actually a limit that we've seen before. All I have to do here is one more thing. I could simplify what's in the brackets. I have n plus 1 over n. So I have n over n is 1, and then I have 1 over n. And this limit, hopefully you recognize, maybe you don't, okay? But this limit we have seen before. This limit just approaches e. And if you don't remember that, that's fine. You go and you introduce a logarithm and you do a bit of L'Hopital's rule. You get rid of that indeterminate form. You're going to get e eventually, but this one is definitely going to be equal to e. And remember that we're doing the ratio test, so we care if that number is larger than 1 or less than 1. In this case, it is larger than 1, and so our series is going to be divergent by the ratio test. And so that's it. Again, I definitely would acknowledge this this whole limit, okay, this whole test would be more complicated if you did not know that this limit was going to be e, but it's definitely manageable. You just need to go and do L'Hopital's rule. So this, these are sort of the more complicated examples that we're looking at for the ratio test. Really, doing the ratio test effectively just comes down to understanding limits. Okay, make sure you don't forget, take that more complicated limit, break it down into easier components by sort of pairing them off with each other, and then the ratio test is going to become much more manageable for you. In the next video, we're moving past the ratio test. We're looking at our very last test, and it is called the root test. At the beginning, it's going to have some very common similarities between with the ratio test, okay, but you're going to see it is itself quite different.